Welcome to G Fun Facts Online. There is an invisible force reshaping our world right now. It's a silent, incredibly slow process that is causing the very ground beneath our feet to rise. This isn't science fiction. It's a geological phenomenon known as isostatic rebound, and it's the Earth's long-delayed reaction to the melting of colossal ice sheets that ended thousands of years ago. Imagine pressing your hand into a foam mattress and then lifting it away. The mattress doesn't spring back instantly, it slowly regains its shape. Our planet is doing the exact same thing, on a much grander scale. This monumental adjustment affects everything from global sea levels to the course of our rivers and the stability of the ground we build on. It's a story about the immense power of ice and the surprising fluidity of the solid Earth. To understand this, we first need to grasp the principle of isostasy. The term, coined in 1882, comes from the Greek for equal standstill, and it describes a state of gravitational balance. The core idea is that the Earth's rigid outer layer, the lithosphere, is essentially floating on a denser, more fluid-like layer beneath it, called the asthenosphere. Think of an iceberg. Most of its mass is hidden under water, supporting the part we see. Similarly, the Earth's crust isn't uniform. The thicker, less dense continental crust, which forms our land masses, floats higher on the asthenosphere. The thinner, denser oceanic crust sits lower, creating the ocean basins. Isostasy is this constant balancing act. If you add a huge amount of weight to the crust, like building a mountain range through tectonic collisions, the crust will sink deeper into the asthenosphere. If you remove weight, through something like erosion, the crust will slowly rise to find a new equilibrium. This is the fundamental mechanism behind the rebound we see today. The trigger for this modern rebound was the Quaternary glaciation, a period of ice ages that began about 2.6 million years ago. During the coldest stretches, particularly the last glacial maximum around 20,000 years ago, vast ice sheets expanded across the northern hemisphere. The scale of this ice is almost impossible to comprehend. The Laurentide ice sheet in North America and the Scandinavian ice sheet in Europe reached thicknesses of up to 4 kilometers, or about 2.5 miles. At their peak, glaciers covered nearly a third of the Earth's land surface. This unimaginable weight exerted enormous pressure on the crust, pushing it down into the mantle. The area around what is now Hudson Bay, which was near the center of the Laurentide ice sheet, is thought to have been depressed by as much as 800 meters. As the crust was pushed down, the viscous material of the asthenosphere was squeezed outwards, creating a raised peripheral bulge around the edges of the ice sheets. At the same time, so much water was locked up in this ice that global sea levels dropped by about 120 meters, exposing huge areas of the continental shelves. Then, as the climate warmed around 700 years ago, the ice began to melt and retreat. This massive weight was lifted from the continents, setting the stage for one of the most significant geological readjustments in recent Earth history, isostatic rebound. But the land didn't just spring back up. The rebound is an incredibly slow process, governed by the properties of the Earth's mantle. While the mantle is solid, over geological time, it behaves like an extremely thick, viscous fluid, like cold honey. The rebound happens in two phases. First, there's an initial, relatively quick elastic uplift, like a compressed spring partially recovering. But the more significant, long-lasting part of the rebound is driven by the slow return flow of that displaced mantle material back underneath the deglaciated area. This viscous flow dictates the overall timescale, which can take many thousands of years to complete. The rate of rebound isn't the same everywhere. It depends on a few key factors. First, the original ice thickness. The thicker the ice, the greater the depression, and the larger the total rebound. That's why areas under the center of the old ice sheets, like Hudson Bay, see the fastest uplift. Second is mantle viscosity. A less viscous or more runny mantle allows material to flow back faster, speeding up the rebound. Finally, the rigidity of the lithosphere itself matters. a more rigid crust will distribute the uplift over a wider area. The speed was greatest right after the ice melted and has been slowing ever since. But even today, the land is still rising at a measurable rate. So how do we measure this slow-motion rise? Scientists use a variety of clever tools. The most precise is the Global Positioning System, or GPS. By setting up a network of fixed GPS receivers, scientists can track changes in elevation with millimeter-level accuracy. For example, a GPS network in Northern Europe has measured peak uplift rates of about 11 millimeters per year in the Gulf of Bothnia between Sweden and Finland. We also use tide gauges. These have measured sea level for centuries. In areas undergoing rebound, the land is rising relative to the sea. This shows up in the data as a local fall in sea level, or at least a rate of sea level rise that is much lower than the global average. Another method involves gravity. As the mantle flows back under the rising crust, it redistributes mass inside the Earth. This causes tiny, subtle changes in the local gravity field, which can be detected by hypersensitive instruments called absolute gravimeters. But perhaps the most compelling evidence comes from the geological record itself. Features that were formed at sea level in the past are now found high and dry. In many parts of the world, you can find raised beaches and ancient shorelines far inland and hundreds of meters above the current sea level. These old beaches, complete with wave-cut platforms and sea caves, are a striking and direct testament to the land's uplift. Similarly, the discovery of marine fossils like seashells in places like Canada's Ottawa River Valley, far from the modern ocean, was one of the earliest clues that led scientists to recognize this phenomenon. Let's look at a few specific places where this is happening. Scandinavia is the classic example. The region was at the heart of the Eurasian ice sheet and is still rising today. The fastest uplift, up to a centimeter per year, is happening around the Gulf of Bothnia. The coastlines of Sweden and Finland are dotted with these raised beaches, and some old harbors have become too shallow for modern ships. Scotland, which had its own ice sheet, also shows dramatic evidence. Raised shore platforms can be found more than 40 meters above the current sea level. And because the uplift was greater in the Central Highlands where the ice was thickest, the entire landmass has been tilted. But the most dramatic rebound on the planet is happening in North America, around Hudson Bay. This was the epicenter of the colossal Laurentide ice sheet. Today, the land along the southern coast of Hudson Bay is rising at a rate of about 1 to 1.3 meters per century. That's over a meter every 100 years. The coastline is visibly advancing, creating vast new stretches of land. Ancient shorelines from a prehistoric sea that flooded the area after the ice melted can now be found up to 250 kilometers inland. And it's not over. It's estimated that the Hudson Bay area still has another 100 meters to rise, a process that will take another 10,000 years. This process is even happening in Antarctica. While still mostly covered in ice, parts of the continent are rebounding in response to past and present ice loss. The Antarctic Peninsula and parts of West Antarctica are experiencing rapid uplift. In the Amundsen Sea area, rebound has been measured at an astonishing rate of up to 4.1 centimeters per year. This slow, inexorable rise has a wide range of environmental consequences. The most significant is its effect on what we call relative sea level. In areas of major uplift, like Hudson Bay, the land is rising faster than the global sea level is. The result is a local fall in sea level. The sea is literally retreating. But remember that peripheral bulge that formed around the ice sheets? Those areas are now slowly subsiding, sinking back down. This subsidence, combined with global sea level rise, leads to an accelerated rate of relative sea level rise. A prime example is the east coast of the United States, which is experiencing higher rates of sea level rise and increased coastal flooding, partly because the land itself is sinking. The rebound also alters the landscape. The differential uplift changes the slope of riverbeds, causing some rivers to change their course or carve deeper into the land. Large lakes in these areas are being tilted as the land rebounds more at one end than the other, causing the lakes to slowly migrate. The shifting stresses in the Earth's crust from all this movement can even trigger earthquakes. These aren't typically as large as earthquakes at tectonic plate boundaries, but they can still be significant, especially near the margins of the former ice sheets, where stress changes are most pronounced. Today, this ancient process is interacting with modern, human-induced climate change, creating a complex picture. The main interaction is with global sea level rise. As we burn fossil fuels, the planet warms, ice sheets melt faster, and the oceans expand. This is causing a global rise in sea level. In regions experiencing strong isostatic uplift, like parts of Scotland and Scandinavia, the rising land can partially or even completely offset this global trend. That's why in some of these places the relative sea level is actually falling. But in areas of isostatic subsidence, like the US East Coast, the sinking land makes the problem of global sea level rise much worse. And here's another layer. The rapid melting of Greenland and Antarctica today is causing a new, contemporary isostatic rebound effect. As these ice sheets lose mass, the land beneath them is already starting to rise. This modern rebound is happening much faster than the rebound from the last ice age. In Antarctica, this rapid uplift might have a slight stabilizing effect on the remaining ice sheet, but it's a complex feedback loop that scientists are still working to understand. This story is far from over. In regions like Hudson Bay, the land will continue to rise for thousands of years. This ongoing rebound will continue to shape our planet, altering coastlines, changing river courses, and affecting everything from coastal management to the stability of our infrastructure. Understanding isostatic rebound isn't just an academic exercise. It is essential for predicting future sea level changes, managing water resources, and ensuring the safety of bridges, dams, and power plants built on this slowly moving ground. The slow rise of the continents is a powerful reminder that the Earth is a dynamic, living planet. It's a process that operates on a timescale that dwarfs human experience, yet its effects are all around us, shaping the world we see today. Isostatic rebound is a profound and ongoing geological drama, a silent testament to the enduring power of ice and the slow, inexorable dance of the Earth's crust. Thanks for listening to Fun Facts Online.